So I'm going to look at some interesting properties of the eigenvalues and eigenfunctions of Hermitian operators. So say we have a Hermitian operator a hat, and let's act it on its nth eigenfunction n, and it's equal to lambda sub n, or lambda n, the nth eigenvalue, times the state n. For this video, I'm going to assume that there's no degeneracies in our system, which for a lot of useful purposes is the case. So let's take the Hermitian conjugate of this equation. Well, by definition, this is Hermitian, so A plus is equal to A. And lambda m is just a number, so it can be pulled out to the side, and all that happens to it is just a complex conjugate. Now let's act it on another state. Could be the same state, could be a different state. An arbitrary eigenfunction of a hat. Act this whole equation on k. Well, since k is also an eigenfunction of a hat, this is just equal to lambda k, and you can pull it out because it's a constant on an operator, just a number. It was lambda n star k. And we can subtract these two equations to get this one. Now if k is equal to n, we have the interesting case that well, that would be pretty redundant if that inner product were 0. So that means that lambda n star is equal to lambda n. In other words, the eigenvalues must be real valued. For state n, or for eigenfunction n and for eigenfunction k, they must have distinct eigenvalues. So lambda n and lambda k should not be equal to each other. So that's non-zero. And that must means that the inner product between n and k, two distinct eigenfunctions of a Hermitian operator, are 0, which means that they're orthogonal to each other. So we can usually write this. We can also show that they are linearly independent from one another. Let's first assume that n and k, two distinct eigenvalues of, or two distinct eigenfunctions of a hat, the Hermitian operator, are linearly dependent, which means that there exists a Cn and a Ck, two constant coefficients that are non-zero, or at least they can't both be 0, such that this linear combination is equal to 0. Well, let's take the inner product with n. Well, n and k are not the same state, and these are orthogonal to each other. So that just goes to 0. And we already said that that's non-zero. So that means that c sub n must be 0 for this to be true. So we can take this whole part out, and this must be 0. Again, it would be redundant if k were 0. So we have to take ck equal 0. So there's no c in ck that's non-trivial that allows us to have a linear combination of n and k that is equal to 0, which means that two arbitrary eigenfunctions of a Hermitian operator are linearly independent from one another. Additionally, let's say that all inner products in our space are, in our function space, or our Hilbert space, for example, are well-defined and finite. Well, in our space is eigenfunctions of the Hermitian operator and other functions. So let's take the inner product with n and some function in the space. Well, this will have to be some finite constant, c, and we'll assume that since all these are distinct, that each corresponds to c sub n. Well, exploiting the orthogonality of the n and k, or of the eigenfunctions of a hat, some arbitrary Hermitian operator, we can just write this as sum over k, c sub k, because that's just the delta of k and n, and then you'll only sum over the n part, so that's just equal to c sub n. Well, we can now remove this inner product part with n and write in other words, with the eigenfunctions of a Hermitian operator, you have a set of functions, or vectors in our, you have a set of functions which are linearly independent and orthogonal to one another, and which you can use in a linear combination to build any other reasonably well-defined function in the space. For that reason, we call them basis functions, or we use them to form a basis for our space. If the eigenfunctions of a Hermitian operator do display this behavior, they're said to form a complete set. So the idea is that an arbitrary function of x can be defined as a linear combination of the eigenfunctions of a Hermitian operator.